مرحبا طلاب. رح أكمل على موضوع second order response characteristic, and we were talking about finding the parameters TP, percent overshoot, TS and TR. Okay? How to find TP? We said that TP is the time at which the system has a peak maximum. You remember that what's the meaning of a maximum? It's maxima and minima. So if you want to find the time and you want to find the maximum value, you go and differentiate the equation or the system. So we have to differentiate the response which we have. You remember that we have the response is like that. This one is a second order system. It's omega n squared. Well, this is the step input. This is C of S. So if I differentiate in Laplace, this will disappear. Okay? It will be SC of S. So if SC of S would be the Laplace transform of C dot, which is this one. If I multiply this by S to get SC of S, which is the differential in time domain, I will get omega n squared S squared plus 2 zeta omega n S plus omega n squared. This one is in Laplace is SC of S. I put it here so that you can see it. Okay? Now, how can I find it? I'm gonna tell you about it, but the detail deriving is not quite easy, or it's not given that much in your book. So you differentiate, you go in the time domain, and you know that this is a peak time. It's not first peak, so you have many peaks. So we'll ended up equating this to 0 and get the time. The time may be n times kada. So we take the first when n equal to 1. So TP, it will be pi over omega n times 1 minus zeta square under the root. This is TP. Okay. Now percent overshoot equal to C max. It's I'll go back with you into the figure. The percent overshoot here, I want that, okay? That one I want. So it's the whole lot here, C max, minus C final over C final, okay? So it will be C max minus C final over C final times 100 because it's a percentage. C max, after we substitute for this TP into C of T, we'll get C max or C of TP equal 1 minus E2 minus zeta pi. This whole thing exponential to this whole lot, okay? I hope it's clear. If you refer to the book, it will be easy, and I'll use it later, so it will be clear. So it will be 1. This is the maximum value. So to find C final in our figure, and for this system is by consider is equal to 1. It's not necessarily equal to 1, but the rule is that one here. Okay? Percent overshoot C max minus C final over C final times 100. If the C final is not 1, it's okay. Put it not 1. It's okay. So we'll have percent overshoot. 1 plus this, which is the C max, minus C final over 1, which is here, C final times 100. So it will be E2 minus zeta pi. This is over 1 minus zeta square under the square root, all C max to all this, okay? Of course, it will be 100 here, okay, if it's a percent overshoot, okay? Notice that this percent overshoot is a function of zeta. This is pi. You don't consider pi. This is just a number. So it is a function of zeta only. So we can say percent overshoot is a function of zeta. I'll give you a graph of percent overshoot against zeta, and I'll finish those, then I'll give you the graph. Settling time is defined as our practical time to reach C steady state or C final, based on 2% criteria as we talked about in first order. But here I'll give it to you without substitution because it's more difficult here. So T of S equal 4 over zeta omega n. And you remember that TS equal 4 times constant. So إذن ينتج عندي TC in this system equal 1 over zeta omega n. Omega n, sorry, I went out the paper. Okay? So this is the time constant in such system when it's complex. It's 1 over the real part of the rule. Now, TR is difficult to find, not like in the first order system. In the first order system, you remember, we substitute for output equal 0.9, then output equal 0.1, then we subtracted the 2 times, we get the realized time. Here, it's not easy. So they go into computer to find it, and there is a graph of zeta against omega n times omega n times ishi. I'll talk to you when I solve a problem for you. I'll let you know about this. But I use rise time 1.8 over omega n. Of course, I'll make you use this in the exam because it's easier. So this is not given in the book. I'll use the one given in the book later in an example. Then I'll because that one is more difficult to find. This is a graph of, as we said, zeta, percent overshoot is a function of zeta. This is the percent overshoot, and this is zeta, of course. You notice that here zeta is increasing. So as zeta increasing, percent overshoot is decreasing. And you know that we found that the percent overshoot is an exponential. So it's exponential going down. If you like, I'll make it darker here. So this is a graph of percent overshoot against zeta, and as we said, as zeta increases, percent overshoot decreases. This is 100%. We don't go more than 100% of this. Let's consider an example. This is a skill assessment 4.5 given g of s equal 361 over s square plus 16s plus 361. He want to find zeta, omega n, ts, tp, tr, of course, and percent overshoot. And I am going to continue with the system. I'll find you the response. Find, hey, like that, find, step, response, so that we can understand how to use this expression we found. So we want to find this first of all, then we find this is an extra, it's not in the question. So we'll solve this question, we'll see that what we can do in so we have we start with we have 2 zeta omega n equal from the transfer function, it's equal to 16. ينتج عندنا انه zeta equal 16 over 2 omega n. Of course omega n equal جذر 3 6 1. This is equal 19. Okay, إذن ينتج zeta equal 2 times 19 ويساوي لنا 0.421. Zeta is dimensionless, don't forget, it's dimensionless. I forgot to put here, this is frequency, so it's rad over second. Right, this is the first thing he required in the question. So we need TS equal 4 over zeta omega n. We have 2 zeta omega n equal 16, then عندنا zeta omega n equal 8. إذن TS equal 4 over 8 equal 0.5 second. Okay? What else? TP. We want TP equal pi over omega n times 1 minus zeta square. I'll divert from here. I'll go on in a procedure so that I'll make use of this data to make to be useful to me to find the response. So what I'm going to do, I'm going to take the denominator, which is a square plus 16s plus 361 equal to 0, get S1, S2, okay? So S1, 2 equal minus 8 plus minus نصف وتحت الجذر what do we have 16 تربيع ناقصا 4 في 3 6 1 okay. To minimize calculation we'll get that S1 2 equal minus 8 plus minus J, because this is greater than this, so this will be negative. So this means that this is complex roots, means that is underdamped. And we can understand it's underdamped because zeta is 0.421, less than 1. So it's underdamped, already we know that. This is 17.234. Now I want to add an information that this TP equal pi over omega d. What's omega d? It's that one, omega n times 1 over zeta square تحت الجذر. ما هي omega d? You know, we said that the system will oscillate. You remember I talked about oscillation, about response, underdamped response. This one, any one of those, okay? So it will oscillate. It has some sinusoidal, damped sinusoid. It will oscillate with a frequency called omega d, okay? Omega d. The frequency omega d is related to omega n. Omega d equal omega n times 1 minus omega zeta square under the, this will be always less than 1 because it's 1 minus something. So omega d is always smaller than omega n. Okay, it's the damped frequency. This is natural undamped frequency. This is a damped frequency. So omega d equal to omega n في 1 ناقصا zeta square. So what's this? The 8. This is, as we saw before above, this is zeta omega n. What's this? This is omega d. Okay, omega d. And you remember we found that omega n equal 19 while omega d is equal 17.234, which is smaller than omega n. So this will be useful for me to write the expression for the response. So I worked like that. إذن TP راح تساوي لنا pi over omega d, which I already found, 17.234, and it's equal, I hope you can see. Let's see, what's omega TP equal pi over 0.1823, of course, second. Now notice that the TP is so small and is always, I told you, it's always less than TS. Look at TS 0.5, this is 0.1, okay? This is TP. What more he want? He want TR. He used an expression. Maybe I'll postpone it now, this expression. I'll give it to you later when you read or you follow up this because too many expressions. So I'll use 1.8 over omega n, and it's equal 1.8 over omega n, which is 19, and it's equal 0.0947 second. Okay, this is TR. This is the easiest expression. It's not in our book, but you can use it now, and later I'll explain to you. Maybe when I solve some question for you, I'll give it to you. Okay. Now we give expression. What's left? He wanted zeta, omega n we found, ts we found, tp we find, tr, and percent overshoot. He wants percent overshoot. What is it? Equal 100 في e to minus zeta pi over 1 minus zeta square تحت الجذر. Okay, this need a bit of calculation. Either you use this or you use the table, but most of the time we use this expression because it gives us, all of us, if we solve it, the same answer. But if we use the table, everyone can look in a different way, so we'll get a different answer. So what I mean, we calculated zeta easily. We can go to the curve, put zeta, and found from here. See? So if I have zeta, something like that, and I have this curve, which is a standard given in the book, I can read the percent overshoot from here, okay? Higher percent overshoot. But sometimes it's not very accurate. So I should calculate it by this. And of course, I think it's easy for you to calculate. I get percent overshoot equal 23.26%. Okay? So I finish with all his requirements in the question. Let's now put the expression for the, so we say step response. C of t. Because zeta is underdamped, I use this expression. As I told you that if we don't, and I solved some question in a class for this type of system, and I told you when we have underdamped, overdamped, critically damped, we solve by partial fraction, and I told you we'll come to this, and we have an expression. This expression is C of t equal 1 minus 1 over beta a to minus zeta omega n في t cosine omega n في t sorry omega n beta في t minus phi. Okay, now I calculated beta equal 1 minus zeta square under the square, and it's equal 1 minus 0.421 هذا كله سكوير وتحت الجذر يطلع لي هذا 0.907. اوكي 1 over beta يطلع لي 1.1024. اوكي I have zeta omega n عندي ساوي لنا 8 and I have omega n في beta omega n times beta is equal omega n في 1 ناقصا زيتا تحت الجذر يساوي لنا omega sorry I'll take this يساوي لنا omega d which we found equal to 17, isn't it? I think 17.234. So I find all the data. Now I can put the expression. I need phi. I need phi. Phi equal tan inverse zeta على beta. You should get it in radian because omega d which you put here is rad al second, and when you put it here rad al second, you will it will be in rad. So use phi in rad better. Okay. So in rad I found this يساوي لنا tan inverse 0.421 over 0.9071. So phi equal equal 0.435 rad. Now I write the expression for the step response. I say C of t equal 1 minus 1 over beta 1.1024 e to minus zeta omega n 8 times t cosine وافتح قوس omega d 17.234 t minus 0.435. Sorry, I came to the edge of the paper. Okay. So it's 1 minus 1.1024, 1.1024, okay. E to minus zeta omega n is 8 times t, cosine omega n beta, it's omega d, which is 17.234 t, minus, this is phi. Phi is, it's here, if it's not clear here, it's here as I found it. So I'll finish here. I'll hope this is enough material for now, and I'll continue from the end of this session. Okay, thank you.